for line integral. Okay? And the statement of the theorem was very important, is that I'm not going to write the full thing, I'm going to just write what we proved, is that if phi is differentiable scalar field, okay, then what it proved is that phi is a differentiable scalar field with a continuous gradient. Okay. So this was continuous, and where in an or on an open connected set. Okay. Then for any 2 points A, B joined by a piecewise smooth path in that open connected set, suppose this is an open connected set and there are 2 points which can be joined by a line, open connected set S, then, okay, and this path is alpha, vector value function. In our end, we have this theorem telling us that if we have this definite integral, okay, which is along the path, to calculate the gradient of the scalar field along the path, it turns out to be phi of b minus a. So that's what we proved. And for the paths are piecewise smooth, so okay, that's the point. It doesn't have to be a continuous smooth path, it could be some point. It doesn't exist, however, there are just only one point. So, and we saw that the integral limits cancel out here. So today we will start with the fundamental theorem of calculus line integral. The first fundamental theorem, the second fundamental theorem, second fundamental, first fundamental, the other way around. First, in calculus, people first learn first fundamental theorem and then second. Here we're doing the other way around, is because introducing this one was easier compared to what we are going to continue to encounter. First fundamental, so this is a theorem. However, I'm not going to prove this theorem, as I said in the last class. I'm going to state it. Theorem for line integral. These are contextual actually. Come to this one first, then this one. Let F be a vector field that is continuous on that and this no, we have to make it. It's open set, so there is a boundary. So because that is continuous on an open connected set S in our end, picking it's also weird, like nobody writes this way, S on side and symbol on side. On our end. So, okay. And assume that the line integral of f, assume that the line integral or vector field is independent of the path of a path in S. Let A be a fixed point of S. Okay. Then we define a scalar field phi on S by where you understand that alpha is the path in any piecewise smooth path in joining A to X. The gradient of phi exists. I would say that phi exists. This is the statement of the theorem. If these things are true, then this gradient exists. And this we used in the last class to prove a theorem for the, well, it was for ordinary integrals, but it's almost the same thing here, line integrals. The statement is almost, except for higher dimensional generalization, it's almost the same. Okay. Yeah. So exists and is equal to the gradient, and is to the, so you know this stuff. So and it's intuitively clear from what we know from ordinary integral, first fundamental theorem of calculus for ordinary integrals. This is true for all x in S. Let us look at this definition of this theorem again. So the theorem tells us that if you have a vector field F, which is continuous on an open connected set, and assume that the line integral of F is independent of the path, okay, then, so this must, so to define this thing, okay, so the right side is an integral and must be path independent to make any sense, actually, so that it becomes a function here, okay, it's a scalar function, but a function to have this, so if you have different, so for a fixed x and a, if you can take many different paths, and if the value depends on which path you take of this integral, then you cannot define a function at that point. So this is a particular point, and this phi should have the definition of a function. And at a particular point, you have a particular value. So it will not be a function if this integral depends on different paths. So you must demand that it is independent of the path. Then with respect to a fixed point A, you must fix one point actually. And then you look at another point, and then you join the line, and on the line, which is, this means on the line you calculate this integral of this vector field, okay, and again for any piecewise smooth path, because you can have segments, and then if this exists, then we say the gradient also exists of this function and is equal to the integrand. So that's the statement of this theorem. So
I have a question.
sure. These are.
Does the you said about piecewise?
Yeah.
Are we taking like say some piecewise sets like S1 and S2? Like you are saying that the gradient is in S, right? Can you the scalar field phi on S? There is a line, yeah.
Yeah.
Then
Yeah.
we define a scalar field line on S. Are we defining multiple S for yeah
Multiple S.
for the
No, and a single. Okay, so it's a connected. No, of course not. There's a single S, a single connected set, and in that connected set, you can have this kind of things.
for single S we can have any piecewise smooth.
Obviously, it's a connected
Okay.
open set. Open set.
We
You
don't need
cannot go. If
multiple.
you, no, you can. Yeah, my well, the whole point is that if you go to another connected set, now that's a good question. Let me think. What do you mean by? Well, here we are considering one S, so everything is in that. So this connected set is something in this. So this is one connect, but this is one. This is another. They're disconnected because as you can see, their overlap is null. So there is one point here. You cannot connect with any point here. So that's the idea of the disconnected.
Yeah.
That's the idea of disconnected set here.
That means the functional dependence is changing for piecewise, and not the domain.
Functional dependence. Um, maybe okay. I don't understand the question actually.
Yeah, and depending on the value of X, I mean, like the subdomain, yes, the dependency will change
I don't understand.
for piecewise, because piecewise values differ from different ranges, right? Because the function is not, it's only valid for
The
different
functions. Okay, so
x's,
I see
right?
what I see what
Right,
you mean. Different
right.
functions.
Yeah,
Different.
yeah.
No, the function is the same. I'm sorry. Function is not changing. Your path is changing. Your path is smooth. I
Right,
mean, piecewise. So you're so if I'm not drawing the function here, I'm drawing the path. These are alphas. Well, okay, you can call them alpha 1, alpha 2, alpha 3, right? These are all smooth paths, however, they are piecewise because there are discontinuities here where, you know, that separated this single path alpha into a lot of segments. Okay? So this is a single function, a vector field, but you are integrating it over some piecewise smooth path. Okay?
Got it.
So, right. So that's so the question. The point is, we actually posed a question to come to this. Why we are not just writing down these theorems, just because they exist. So there is a good motivation why we are studying these theorems. That's what okay. So that's why probably the second fundamental theorem came first, and then first. The reason was that we posed a question that which of the vector fields, if you integrate over them, so we define line integrals for vector fields, and we ask the question that which of the vector fields do not depend on the path. So we define this line integral, remember last class, and we ask the question which of these. So we ask the question for a definite integral. Which of this kind, which of the vector fields are independent of the path? Okay, we ask this kind of questions, and that's why this question led us to the second fundamental theorem. That's why second we studied first instead of the first fundamental theorem to answer this question. That okay, these are actually very special type of vector fields which are gradient of um, some scalar field. And now we met first fundamental theorem for line integrals, which kind of complements. So it is not okay. So first fundamental is that you have one point fixed and another point can be any other point. Then you can express the integrand as a derivative of the scalar field. So yeah. So this kind of establishes the fact that the antiderivative integral is an antiderivative. This derivative then. Now, all right. So now we again go back to the question that which vector fields um, are path independent. So we have to find, we're just saying that that we have a hint that this kind of expressions for vector fields are path independent because we found it from second fundamental theorem of calculus for line integral. However, we want to find a neat way of stating this fact that when or what scenarios, okay, that the vector field is actually path independent, is actually the gradient of phi. I mean the same thing. Okay. So that means we want to pose this question in a necessary and sufficient condition for a vector field to be a gradient. Let's see. So this will be just all these facts that we covered here packed into a theorem, and a nice theorem or a nice condition, you might like to say. So this is our theorem number 2 for the day. So can you follow the thread, what I'm saying? And you see WSA are necessary and sufficient condition for for a vector field to be a gradient of a scalar. That's the name of the theorem. So what is the theorem then? So let F be a vector field and which is continuous on an open, which is continuous on an open connected set S, which is in Rn. Then the following three statements the following statements are equivalent. Sometimes this thing is expressed as like TF, the following TFSE, the following statements are equivalent. TFSE maybe. The following assertions are equivalent. So sometimes people write TFAE, assertions. Here I'm writing statements. Yes. Anyways, that's little. So what are those? What are these statements? So F is the gradient of some. So now the scalar field will be called a potential function. Okay? Some potential function, pretty much inspired from physics. So the potential function in physics is like, you remember the electric field is negative of the scalar potential, right? So in electrostatics, so it's kind of inspired by it. So F is the gradient of some potential function in S. That's one statement. Let me call them A. B is the line integral of F is independent. Line integral of F is independent of path. Path in S and line integral of F around any closed smooth Smooth means piecewise smooth path is 0 in S. So they're quite reasonable statements, and they all mean the same thing. So that's that's the necessary and sufficient condition for a vector field to be a gradient. So we have already actually met A and B. So we know that A implies B. A implies B or B implies C. The line integral is even of path, then F is the gradient of some potential function. That is theorem, this theorem, right? So B implies A. We started here that we said that if the path, if you have the vector field, the line integral of the vector field is independent of the path, then you have this expression that the vector field is actually a gradient. So we have met this. B goes to A. We have already proved it because of theorem 1. So the value of this theorem, so you might ask, okay, if we have proved this, so why am I stating it again? The reason is that you see that these are much more, so these are much more finely stated, precise conditions. Okay, these statements are, when you put it this way, they become a theorem, and they actually enforce you to see that there is nothing else beyond it. Okay, that's why. Okay, necessary and sufficient condition. It covers everything that you need to know about a vector field being a gradient of a potential function. So B implies A, then from A we see that F is the gradient of some potential function and the line integral is 0. Actually this is the statement of theorem 2, this one. Okay, so because this exists on the open set, then this is, so if this is true, then for a closed, so this is independent of the path. We have proved it, right? We proved it for the path and becomes this. So if you just extend it a little bit, we did in the last class, if you consider a closed loop or closed path, then the integral is 0. Okay. So given f is a gradient of some potential function, the line integral is 0. So therefore, A to C is also proven by theorem 1. Okay. So what is left to show is C implies B. So we want to show that C actually implies B. So B implies A implies C. So we have to find a connection between C and B. Okay, that is C implies B, just to close the gap. Okay, is it okay? Can you? Is it? Everyone agrees?
Yeah, yeah.
So the non-trivial part of this proof is okay, that C implies B. The integral is 0, then you have to prove that the line integral is half, and it can be easily done. Okay, using what we already know. So you can say we have two piecewise smooth curves in S with the same endpoints. So the proof, we're going to prove. So let me start writing it. No, so we only need to show C implies B. So so consider two piecewise smooth curves um, C1 and C2 in S with the same endpoints. Okay, so let C1 be the graph of alpha on this interval AB, and C2 be the graph of alpha on interval CD. Define. So we have this. Okay. Now define a new function called gamma. Actually, it's going to be a vector level function, so which combines these two. So what is the idea here? We are trying to prove. We're trying to prove the fact that if the line integral is 0, then the line integral is independent of the path. Well, that's what I want to show. So if it is independent of the path, which means that if I compute it in C1 and if I compute it in C2, along C1 and along C2, then it should be the same, right? So the strategy is I consider a closed loop with C1 and C2. Okay, I consider a closed loop with C1 and C2. Okay, this way. That's the idea, and this is equal to 0 because that's the C statement here. That's telling us. Then you're going to part it out, C1 and minus C2. It will be minus because it's going the opposite side, equal to 0, and from there we show that C1 equal to C2. And because C1, C2 are arbitrary, this can be done for any other paths. Okay? So therefore, the integral is actually independent of path. Okay? That's what we're trying to establish. So, okay. So this you can say sketch of the proof. Okay, so gamma of t is alpha of t if our t belongs in this interval, and beta of e plus d minus t if t, I'm sorry, if t belongs into b comma b plus d minus. Why is that? Well, you want them to be having, you want to have them the same endpoints. So that's why you require it this way. You want to have the same endpoints. Therefore, so this path starts at A and ends at B. It starts at A, ends at B. Then another path, so this is the alpha path. So another path starts at B. So you start B plus D minus C. If you plug in here, uh, this would be, so this B plus D minus C. If you plug in here, or you would find this point to be, oh, let me check. So if I want to find, this is a B plus D minus C, right? If I, so, right, man, I have to identify 2 points, haven't I? So if I
Bhaiya, if we
plug in
and
B, it would be D. Yeah. If you plug in B, it would be D, right? If you plug in B, it would be beta of D. If you plug in B, and if you plug in this, it would be beta of C, I think, right?
yeah, Bhaiya, aren't C and D are two different points than A and B? Then
Yeah, that's what I'm saying. Yeah,
how come we are
C
we
and D are
showed
not
that?
different points. They're different intervals. They're not different points. So I am actually
Okay.
doing one bad thing. You can say that my bad thing is that I have done a bad thing. Yeah, thank you. That's why it's not. I had to ultimately change what I'm saying because these. Well, I can still call them AB, but I have to give them this factor. So C and D, they are also, okay, so this is actually B vector and this is actually A vector. These are intervals, right? The intervals are not realized in the space. And
Yeah,
in
yeah,
space,
yeah. That is so.
so you have to identify them, okay, in this way. So your B of D is B. So what is alpha of A? Alpha of A, we already met this A vector, and alpha of B is B vector.
Okay, now I got.
Sorry, my notation made it wrong. Yeah, now it should be clear. But and also I have to close the loop. So this is going the other way around. This is our beta. So when you do that, then of course gamma now describes a closed curve. This describes a closed curve which is made out of two curves. This is your C1. This is your C2. So, well, you can say it is negative of C2 because of the way it's defined here. Okay, so gamma defines a closed curve. Okay. So you can call it a C, which is made out of C1 and C2, and you compute this thing. And this is 0 because of C. This C is the statement of the theorem. Okay, C. So then now you can easily show that it is actually, just break it apart and you can easily show. Okay. So there is a very good remark to this theorem. There's a remark, very important remark. Suppose you found uh, an integral of a vector field, okay, and you found this to be 0 for say one curve, or for actually the stronger condition I'm going to write for infinitely many uh, paths, of course closed paths. You found this to be 0. Okay, then if I ask you the question, then can I write f to be, f? Can I say that f is a gradient? Is this true? Can I say this?
Yeah,
No, I cannot.
why not?
The turns out you can have infinitely many but similar paths, not for any path. Any path and infinitely many paths are not the same, because you can have, say, closed paths centered at the same concentric curves, right? You can have concentric
I
curves,
see.
concentric closed paths where f integral is 0, the line integral of f is 0. However, uh, f is 0. However, you take another path, okay? You take another wiggly path, whatever, then you see this is not 0. Okay?
That means
So
we can have parts of level sets which can be zero, infinite number of level sets.
yeah, you can, but that is not part of the theorem, right? But that can be, obviously, there is no constraint, right? You can find it, right? If there is nothing forbidding it, if you look for example, you should be able to find something, right? There is nothing as far as we know. So if there is something we don't know, then it is a matter of investigation. Here, as far as we know, there is no constraint in finding such paths where the integral might be. So you may find one path, you may find similar paths. So the trick is to actually do it for general paths, okay, which doesn't have a symmetry, right? So this kind of paths have a symmetry. This is a special type of paths, right? So you can consider a special type of infinite number of paths, and you may be misguided, right? Okay, so it should be
Mm.
true for any path. That's the message. Okay. So
Sorry, I have a question.
yeah,
So does it mean that if we don't have any smooth path, then the line integral won't be 0? I mean,
you can always find.
if the
The
path is
theorem,
not
yeah,
smooth, right?
yeah. My theorem is that you should be able to find. I'm sorry, I said always. That's not true. I
I
mean,
think we can draw some boxes, concentric boxes, then we can also show that there are infinite number of closed paths instead of
yeah.
circles.
That depends on the problem. Okay, circle is an example. So you have an example. For example, let me give you the example. Yeah, you can find boxes as well. That's for another type of function. Yeah. So this is an example for, say, you have a vector field given by, say, xi plus xyj. So these kind of vector fields, if you integrate it over a circle, then you see this is actually 0. So the question was, Mr. Focus asked, is that if we cannot find a smooth path, is that the question?
Yeah, I mean, the point is, when, if I understood correctly, I mean, for any closed path, the integral should be 0, right? Is
No,
that correct?
no. I no. For any, okay, I didn't quite agree. For any, for infinitely many closed smooth paths,
Smooth path, okay.
it's always smooth. So as a theorem statement, you see it's smooth everywhere.
Okay.
So smooth means, well, we are using the word smooth, right?
Smooth means
Smooth
it
means
has
actually,
gradient, right?
yeah, smooth means it's actually infinitely differentiable.
Yeah, okay.
When we say smooth, it means it's infinitely differentiable.
Okay.
It's a very strong condition. Very nice path. So, any other questions? So, if none, then let's move ahead. So, right. So there is a, so even though this, so this theorem is actually establishes necessary and sufficient condition, it's not very useful. This theorem is not very useful here because it's not very useful for practicing it. Practicing, you want to, so if you are given an arbitrary vector field, you want to check if it is actually a gradient of a scalar. This theorem is not that helpful. It asks you to go through a lot of tests and a lot of involved checks. You see, one type of check will not. There are also caveats. Caveats where you can misguide it as well. This is not very good in sorting the vector field. Look for something better, something improved. There is an improved test for it. So that will go by theorem, other theorem, third theorem of the day, the third or second theorem. Third theorem of the day. Necessary condition vector field. It's an alternative condition for a vector field gradient of a scalar field. I'm using symbolics because I don't want to write too much. And this is an alternative to what we have met before. So the statement goes like this, that obviously you have a vector field. Now we will talk in terms of components. And the continuously.
Excuse me. Sorry for my gap in this. So in the past one, it was necessary and sufficient, right? So that means one was enough. So, but here it is only necessary. So I just forgot.
Yeah, it's an alternative necessary condition. Yeah, this is. Yeah.
So if it is only
necessary means that you go from.
It is lower.
It's an if part.
If
okay,
part. If part. Okay.
This is the if
and
part.
the necessary and
sufficient is the
else part.
Yeah. So sufficient is the other part.
But
it's only if part.
Necessary and sufficient. If it is both, then what happens?
If necessary, then equality. A implies B.
Oh, implies. Okay.
B A.
Okay. So the previous one was
So
implication.
So that is the A equal to B.
Oh, okay.
Yeah. These are all implications. Right? If A implies B implies that, then A equal to B.
Okay.
There are also other cases like contradiction. There is this. So if
so it is both. The arrow goes both ways. Right? Arrow goes both ways. Right. Yeah. And B also implies.
Yeah. Something like that. Yeah. Let me not. Okay. I will post a few things about.
No, sure. I'll just I'll find out.
This is important there as well. That's important. Okay. Okay. The logic is logic. There is no mathematics. If you make it precise, that though there are a lot of problems in mathematics. These are very involved stuff. Usually, normal people do not go into mathematics. Normal working mathematicians still going so much. It's it's a different. It's a lot of things. Maybe it's a discussion for the day.
Okay, sorry to interrupt you. Yeah, please go ahead. Yeah, thank you.
No, yeah, that's fine. Yeah. Differential factors. Now I was thinking of there are a lot of puzzles. We have heard of different Gaussian. Those are analogous that any care of 3% as well as kind of questions. So as so this is a continuous differential field, right? And as if it's on F is a gradient. So differentiable, expecting it to be one differentiable. And when we say differentiable, it's just on the open set. Please remember that. When you say differentiable, you have to mention where it is differentiable. In a region. So if f is, unless there are entire functions which are differentiable everywhere, you have to mention where it is differentiable. So if f is, so for example, what Tibra Ali in the last class asked, the f of x equal to x, where is it differentiable? It is differentiable everywhere, right? The entire function. Where it is where is differentiable? It's differentiable everywhere. Similarly, other functions are different. Sine function, log, whatever, log function, sine function. If f is a gradient phi on f, then this is the statement that difj x should be equal to dj fi x, where I comma j rounds from 1 to n, and or any x in s. That's the sense. So a vector field has a number of components. A vector differential means the components are also differential on a concept. Then f is the gradient on f. Yeah, sorry, not then. If, so this is first assumption, and also other assumption is gradient, then this is true. So to have gradient, okay, this is another assumption. That's assumption. So the proof of this fact is almost immediate. So you start with the fact that it's an assumption that this is true. So start with it. So let a vector field, which is defined this way, which really means, if you write it, which means component-wise, this means this. Each component is actually a partial derivative phi, where obviously it's one of the indices. And what is derivative? You add only with derivative. So this, I'm going to, it's the same thing. You don't change the symbol. I'm going to call it DJ. The same thing. You can do the same thing. Because these are the coordinate. The directions are Okay, these are the coordinate function. So that's one equation. Then you can do the other way around. You can say, okay, this j, I'm going to consider it be I, and then I apply with j. Then you get a different equation. Equation 2. Here we're calling it a j, but you, well, with an example of it. Say f2 is equal to d25. You apply d1 on it, then you get this. Then you have f1 equal to d15, then you apply d2 on it. So this is the analogs of this thing. Okay. And obviously, a and I and j can be the same. Then it is trivially true what we want to prove. But okay. Now, what we have demanded, we demanded that the vector field is continuously differentiable. Continuously, it's not just differentiable, it's continuously. So differentiable is continuous. Isn't that redundant? If we say differentiable, it is continuous. Differentiable means. Anyway, so from earlier some of the theorems we can come to this conclusion. So from one end, because the continuous partial derivative exists, the mixed partial derivative is equal. Like the di is dj. Because the partial derivative that exists. So how does it help us? It is a very useful check. So this you are sure that that has a gradient of scalar flow. Example Apostle has is this, that we have a field of R2, something like this, for yj, and if you apply d2 f1, you find 3x squared. You can see that f1 is this one. If you apply d2, you get 3x squared, and if you want f2, so this is your f2, this is your f1, and f2 you apply d1, which you get 2xy, and obviously they are not same except is equal to 0 or usually construction is going on around. Except x equal to 0 or x equal to what? X equal to, well, only x equal to, x equal to 0 will be true. If I consider,
Sorry, can I ask one question?
yeah, sure, obviously.
D2 means, because I get mixed up with this, D2 is not second derivative, right?
D2
D2
is no. It is respect to y.
Oh, okay.
D2 means it's with respect to y.
I just get confused. Yeah, okay. Yeah.
It is actually what we have been using with respect to x. This is what we've been using for for a very long time.
Okay, sorry.
Yeah, so that's fine. Yeah. So we haven't changed the notation. If you have if you have a 2 up, then you might be thinking that this might be actually.
Yeah, okay. I just positionally I got confused.
Yeah. So only x equal to 0 it actually works. You say that these two are equal only if x equal to 0. I can't say maybe one has to check. Maybe at some other points it can be equal. Can it be? So let us set them equal. 3x squared is 2xy. If I set the cancel x, say x not equal to 0, then 3x equal to twice y. So so you have to do, yeah, obviously, for some bunch of points, x, y values satisfy this condition. For them, this would be true, but not for in general, right? In general, these two are not same. Okay. So yeah, this defines a line, right? So there are infinite number of points for which this is true.
Yeah.
One has to ability to have fun, but still this is not. Still, this is not.
So this is not a gradient on open set.
It is not. It's still not a gradient.
A gradient on any open set.
Even though you can make it work for infinite number of points.
Right.
Sorry. There's another example. It's a very nice example. This one. Okay, so I also want to plot this one. So f of x comma y, this is like minus y divided by x square plus y square I, and y becomes 8 of x. And then headless. Okay, good. So if you look at it, does it look like a gradient? Do you think that this can be a gradient? What is your gut feeling when you look at this?
Is it minus before y in I?
Yes, minus,
yes. Yeah, there is a minus here. Thank you. Finding it out correctly. So let's see. What do you want to do on the graph? We need to draw a graph. Let's try to plot this. We have minus y divided by look at this graph. This is the thing I was looking for. I think it's visible, right? Can you see it?
Yeah, now better.
Thank you. This is a. So, does it look like a gradient? This has a circulatory motion. This looks like a curl. This looks like more of a curl than a gradient.
Yeah. It's more of a curve.
So this is not. So this is a rotation. So these things are this kind of expression is telling you something about rotation, and this cannot be just looking at the expression. You can see that this is not going to be a gradient. Okay. So this is
So
a
that
homework to check that.
function cannot be written as a gradient form.
I'm sorry.
So if the vector function f of xy cannot be written in vector form, gradient form, right?
Right. Right. That's what I'm saying. It's not a gradient here. So your gradient is, what is a gradient? So you have a integral curve. Then these are like this, right? A
Yeah,
gradient
yeah,
is perpendicular to the tangents, right? So look at this
yeah,
graph. This is the integral curves. This is the integral curve, right? So this is the integral curve, and the integral curves are actually they are this vector field is actually following the integral curves like that. Okay, they're not perpendicular to them, right? So what they're supposed to do? So you have two integral curves, right? The gradient is supposed to tell you the maximal change. Okay. So what is the integral curve? So there is a these are level curves, right? So this is f equal to
yeah,
c1. This is f equal to c2. This is what is meant by integral curves, right? So
yeah,
gradient is supposed to tell you the maximum changes or maximum decrease, right, from a particular value, right?
yeah, yeah,
So here C3 is less than C1 is less than C2. So it tells you it's increasing in this direction, decreasing in this direction. And these directions are maximal increase and maximal decrease. So that's the way gradient works. But if you have an integral curves and like this for the vector fields, which are following the integral curves like this, that means they are tangentially following it. Actually, this is never going to be. This is not telling you increase or decrease in the integral curves, right? It's actually following
yeah,
it.
yeah. It's
So
just pointing
it's
to that
rotation.
curve.
It's actually rotational. You can see that
Yeah.
it's actually rotational. So there's a rotational vector flow.
I think I have seen these curves in fluid dynamics a lot.
Yeah. They are related to curve. Exactly. In fluid dynamics,
I think
they
they are
are.
called vortexes in fluid
Yeah,
dynamics.
they're vortices. So the rotation is the generator of vortices. So a necessary condition for vortices is that the curl of the velocity vector is non-zero. Okay. So your vortice is defined by half of this.
Yeah,
So
yeah, yeah.
this is the what we have. So there is another way to show that this is not a gradient, bit more algebraic gymnastic rather than insight, and that is you can calculate using the theorem. You can prove it actually. And this is also very important. Sometimes you just cannot. The problem is so hard that you cannot see through things. So sometimes it's important to know the technical aspects so that you can prove them, even though it's hard to find an explanation for them. So you calculate this thing, and if this is zero, then there is a possibility that this is a gradient. Right? So if it is non-zero for a particular, so what is the test? Okay? What is the test? The test is if this is not zero for a one path, okay? For a one path, I find this is non-zero. So what can I conclude?
It is not a gradient.
It's not a gradient. For one path, I find it is not. But that's the power of the test. It's not the other way around. Power is not the other way around. If you find it for one path that it is zero, you cannot say that it is to assure. You cannot assure that this is a gradient. But if you for a one path you say this is not zero, then this is definitely not a gradient. So this is this is the test we are going to do for this one. So we will compute it along the circle, which is the symmetry, which is the integral curve symmetry, right here. Circle. So we take a circle and you integrate along it, okay, and see what we find. And so a circle is parameterized by what? By trigonometric functions, right?
I think it will be sine of t. Sine of
Yeah,
t, comma
sine of
cos of t, sine of t
I
only.
plus cos of.
It doesn't matter. Okay.
Um, yeah, I can end up with a, yeah, it doesn't matter, but okay. And here's the fact. It does, well, depends on how you, cos of ti and sine of tj. Does it not matter? It, right? Is the t just
Yeah, yeah,
t with respect to this? Yeah. Thank
yeah.
you. Yeah. So what we do is that f we compute this thing, and we have an x over actually f is nothing but
F prime,
if you are
F alpha
computing it
prime.
along it, so alpha instead of can be alpha, we can make also it means, right? So okay. So what is alpha prime? Alpha prime is nothing but minus cos t and minus sin t, sorry, minus sin t and cos t dt. And what is our f? Our f is, so we want to write f in a suggestive manner. So I'm going to plug in, so f is a vector field, which is a function which is over the, along the curve, this. That means f is going to take these things as input, minus sin t, not minus, alpha of t, this one is input, so it will be cos t and sin. So this part would be, so x square plus y square is 1, right? So if you look at this function, x square plus y square is 1 because cos square t plus sin square t is equal to 1, so it's 1. So upstairs you have minus y, that means minus sin t, and this is cos t, right? So can you follow what I'm,
Yeah, yeah, yeah.
can everyone follow? Please ask me a question if you can't follow.
You're right. We can follow. It's in the book, I guess.
So this is going to be too far. So yeah. Um, so the conclusion is obviously f is not using our theorem 2. Okay. So so what we have used here, mathematical logic, what we used here is that we know that C implies A, right? This is a, so we said that C was the closed loop integral should be 0. Then if closed is equal to 0, then this implies that f is a delta operator. So what we have implied here is that if this is not true, so this is a negation operator. If this is not true, this implies that this is also not true. If A implies B, then not A implies not B. This is by this logic we are claiming that. Okay, so now the next topic is special methods for constructing potential functions. Um, um, so we want to construct potential functions, and as you see, it's not easy actually, because we can find infinite number of paths where the integral is 0. Still, you cannot say. So we have to find more interesting constructions. Constructing potential functions. I'm running behind on time. Let's go. So this is another topic, maybe topic 2 for today. All these things are topic 1. So, right, these are all topic 1. So, okay, so there are a few constructions. One of the constructions is that if f is a continuous gradient on an open set, then open connected set, then we know that the f is independent of the path, okay, and then so so we can consider two paths, okay, whose initial points are different. Okay, so but they only differ by an edit by a constant. If you start for, okay, so if f, so that the statement is this: if f has continuous gradient on S, here I am not writing everything, S means open connected set S, then F is independent of the path that you take. Now, you can define a potential like this, right? Now you can also define the same potential, but it depends on the X, right? It doesn't, okay, so you, okay, there is some dependence on A, right? You cannot say it doesn't depend on A because it has a limit. So you could ask, okay, I can take the path from another point. What's the big deal, you might ask? So is it the same, is it defining the same thing? The question is. Actually, it is defining a different thing. It's just not defining the same. Because logically, you would say, okay, the phi of x, because this is an integral, it depends on both the limit points. If I mess up with the limit point, I should not get the same function, the same scalar field. I should get a different scalar. Okay? So first thing is, it's not the same scalar field, just from looking at the integral limit, and you can say that. What do you expect to behave? However, you can ask phi x minus psi x. What is this? Their difference. You can ask, what is the difference? What is the difference? How much they differ? And it turns out they differ. Yeah, question.
No.
It turns out that they differ by a constant. Okay, and this is also intuitively clear because you are evaluating them at the same x of the same vector field, and this is independent of path already, independent of the path taken. So it only depends on the endpoints. So if you mess up the endpoints, you better get something which is just different. So you're getting something which is just different from phi by an additive constant, some additive constant. So this is the reasoning we are going to follow here for the first construction. It goes by the name of, so let me call this one, construction of phi on an open rectangle. Okay. Now, so let me draw a diagram and this will become clear. Even though this is open, for my simplicity, I'm drawing this, okay? And see if I can make it open.
Yeah, I mean, the book has two sides solid, two sides dotted. But that's okay,
Yeah. Confused, yeah. Isn't it open rectangle?
It is open rectangle, but if you look at apostle,
Yeah, he has this said. Yeah.
Two solid lines and two dotted lines. Yeah.
Yeah, I think he meant that to different paths.
Oh, okay, okay.
So his choices are very, his choices are very weird.
Yeah.
Anyways,
It's from 1975, I guess, right? Do they have
yeah,
any later version? They don't, no?
I'm not sure, but he wrote, but the book is very well written.
Yeah,
Just
no doubt.
just
No doubt.
annoying. Some of the things are just he just want to mess with people. I think
True.
he just want to mess with people. Nothing else.
Yeah. And
So
he's
in
very
physics,
successful. At least
yeah,
with me, he's very successful.
yeah, he's very successful. So in physics, this is famous for Steven Weinberg.
Yeah.
Steve writes these books, amazing books. He's a scholar. He knows all the nitty-gritty details of QFT. So Steve wrote this. He's now he's not alive. He's not with us anymore. But Steve wrote these amazing books. Excellent explanation. His notations are horrible. So whoever goes to read them, it's a nightmare for them.
Yeah.
Well, actually not for everyone. People enjoy it. But class of people that enjoy it are like Weinberg. So we denote these coordinates on this open rectangle, and we consider two paths. One path we'll consider this way. This is this. One path will be this way. This is one direction. And another path we'll consider this way. Reaching to the right upper corner. So so let us go ahead and define these paths. Okay. So for horizontal segment, this path, I define it this way. We apostrophe quoting from it. So this is so what is changing along this? X is changing, B is fixed. So you see B is fixed, X is changing, and X is changing from where to where? This is actually ranging from these points are this is a bit of a tricky. It's a bit of these points are actually included. So what is the question about open rectangle? You need to have those points, and you're following on the boundary on an open rectangle. What do you mean by open rectangle? Sure. Is this an open rectangle? Because my endpoints will be needed. I need to include those endpoints. So I can work on open rectangle, but I'm on the boundary of it. So open means it doesn't have a boundary, but I'm actually working on the boundary.
I don't think he has defined it.
Yeah, he needs an open connected set.
Yeah, but open rectangle, the definition of open rectangle is not there.
Has continuous gradient on an open rectangle in R. What do you mean by an open rectangle? It is the interior of it. So maybe, I don't know, maybe he has this open line, I don't know. So it has to be bigger than this. So if you have an open rectangular region, inside he has this, inside inside is a connected set. So he can consider rectangle there. Okay? I think this, if I consider this, there is nothing wrong. But
so
I have
more like
yeah.
a conception, not so much of like geometric interpretation.
Yeah, it's geometric. It is geometric. But however, if I consider this rectangle, if I consider this rectangle as an open connected set, and
okay.
I'm considering the edges of this rectangle, right?
Right.
And I'm going to use, I'm going to calculate my f line integral on this rectangle, which has this endpoints and etc.
Okay, fine.
So
So can you also like explain by contradiction, meaning in that case there should be a closed rectangle as well, right? Then what will be a closed rectangle?
yeah, closed rectangle means you just have this all the boundary is there. Rectangle means that rectangle is boundary, right? So the boundary is there.
So by default, any rectangle is a closed rectangle.
Yeah, but the theorem, no, actually, yeah, yeah, from looking at this diagram and how he, okay, so let me try to see. F is continuous, F is a continuous gradient on an open rectangle in R. F is a continuous gradient in an open rectangle, okay. Maybe F is a continuous gradient. What am I going to use there if it has an O? Let us look at theorem 1. Theorem 1 told us that continuous gradient after there. Theorem 1 তাহলে what is saying that F is a continuous gradient on an open connected set. But path is in S. Oh, that is the trick. That is the caveat. Obviously, the path is in S. So clearly, now there is this huge problem. Clearly, I cannot do this, right? If this is my S, okay, I clearly cannot include the endpoints. I clearly cannot consider the path because this is not in S. Do you see the point? The boundary is not in S. If this is an open set, okay, the boundary is not there. So the open set must be a little bit bigger than that, which contains this rectangle. Okay.
Okay. So it should be, I mean, exterior of this.
Yeah, it must be bigger than the rectangle itself, but it must contain the rectangle.
Yes.
Okay. So what is the minimum shape that can contain the rectangle and connected set? So a rectangle itself, right?
Mm-hmm.
So this is what I try to draw here. Okay. So
I mean the thin dotted line.
Thin dotted lines, yeah.
That's the set.
This is the S.
Yeah.
And the interior of it is the.
Now it makes sense, yeah. Okay.
So now we can proceed with this thing. Okay, so we have the horizontal line segment, and what is the vertical line segment? Vertical line segment is this one. This is our alpha here. So what is our beta? So well, how are we going to call that one as alpha as well? I'm going to call it a beta, just to distinguish them. We have a lot of Greek letters available. So here x is staying fixed, and our y is changing. Again, t will be to y. You can see y is changing along this. So now we go ahead and compute the line integral along this piecewise continuous, smooth continuous functions or paths. Okay, this is this one. So phi is going to be f dot d. Okay, so it's going to be d alpha but computationally it is much better if I use this. So what is this? So so f has two components, f1 and f2. f1I plus f function. This is nothing but f1 alpha. So okay. So alpha prime. We have to say which path I'm following. No? So alpha. Okay, so this thing has two pieces actually. If I consider the whole path from here to here, there are two pieces. So for f1 along the horizontal piece would be this piece is not going to pay any part because I dot j would be 0. So you have a f1 dt integrated from a to x, and then so the question remains if I compute it for so I do it for this path along this direction. So I have to write it much better than that. Do better than that. So okay, before going to alpha prime, let's we could keep alpha prime. I don't want to because it's going to be just a bit more obscure. I have to carry some factors. So I'm going to call this path 1. So this is say C1. So this is C1 path this way. So what I can do, I can say this is C1 horizontal. This is C1 vertical. Does it make sense? So once I'm computing along this C1 horizontal and then I'm doing along C1 vertical. Does it make sense?
Yeah.
By this separation. So then it becomes so for this so I should use alpha beta differently, no? For vertical I should use beta. Then you can go ahead and apply okay. These are and f is f1 and alpha prime is going to be just I vector prime. And then I'm applying from here to here I'm applying this. So alpha prime is
Wouldn't there be a T?
yeah, you should be able to ask me why yeah, so integral okay, so this should yeah
Oh
where is
yeah,
the
I
T?
get it. I got my bad.
Yeah, that's all right, no worries, but okay, so yeah. So what happens when you have a B and F2? My question is you still have a dot product which is 0 obviously, so that doesn't count. Yeah, that's no question. Can you follow?
Yeah.
Can everybody follow?
Sorry, I couldn't, especially while in this.
Yeah.
But the book says a bit. Can you just show the book page and explain from the, if you don't mind?
No, I can. I am not. I don't mind. Yeah, it's 343.
Yeah. Can you just open it on your screen?
He didn't do it. Yeah, he didn't do this way.
Yeah.
He just wrote. He wrote down the answer. So I'm not following. The answer will turn out to be same, but he didn't do the bits right. He didn't do the bits. Can you? Okay. So I have.
AX, DB, and then.
But can you follow what I'm doing? Apart from apostrophe.
I was just trying to reconcile, but there I got lost.
Do not reconcile first. Okay, it will be confusing. First, try to logically see if I'm making something which is not okay. Doesn't you don't get it or it's something is not right.
I was trying to flipping between screens and then got confused.
Yeah, this will be confusing then because I'm not strictly always following that.
Okay. So I was flipping screens actually. Yeah.
So here I'm using this thing that alpha prime dt at a to x plus it would be alpha prime beta prime dt. I think it's b to y, right? Is it okay? This line to this line?
Yes.
And then if I look at alpha prime, then I see that there is only this component survives. This goes to 0. So I have f1 because I have f1 a2 x dt plus beta prime. Beta prime means derivative of beta with respect to t. So only j survives, which is f2. Now you can find the same answer in apostrophe. So yeah, so we get it. Then what we do is, okay, so we have this expression. Now this is for one particular path we followed. This is along C1. So this is along this red line. But we could do it also for this line as well, right? We can do it for the C2. So what we would get for C2? So, okay. So for C2, should I call it a phi or not? Okay. So I'm starting from the same starting point, A, B, and then I'm going here. So I should get the same actually. Here I have the same starting point. So I should get the same, right? If I go from here to here and I go from here to there, I should get the same, right? It's just I'm taking two different routes. So here I expect it to be phi from the independence of path. Okay, I'm changing the color as well. So if you do the same analysis that we did, so here you have to consider a vertical alpha. So you got alpha here would be what? So your A is fixed, and you have a Tj where T is bounded to B and Y. Similarly, you consider for this path called beta, blue beta, which is your here A is changing, so it's Ti plus Yj, where T is bounded to A to X. And you do the same analysis. However, here you first go from B to Y. So you will find here B to Y, and it should be F2 dt plus F1 dt, and you're shifting from A to X. Okay? Yeah. So this should be true. Okay, the both of them should be true. Both of them should be equal because they're independent of the path. Okay. Is it all right? So why we have to consider? So what is the point here? Did you understand what the point is? What the point I'm trying to make? So we are looking for special methods for constructing potential functions. We saw that if our starting points are different, then we will find different potential actually. Okay, which are related by some constant c, but still they're different, right? I mean, there is still a constant. Okay, every time you change the endpoint, you will end up with another constant. So, okay, so if you want to find exactly phi, you want to start from the same point. So you want to do it in a rectangle. Does it make sense? And choose two different paths.
I think an example would be like taking gravity with respect to the surface and with respect to the center of Earth.
Yeah, I don't want to. Yeah, I get it, but I wouldn't. Yeah, you're right, but I don't want to go into those subtleties. There could be subtleties there, but mathematically doesn't make sense. But explicit examples are always difficult. Can you come up with a mathematical example? Like this is a mathematical example, right?
Yeah.
So you
I
can say
think
this for the.
also state functions of thermodynamics can also be an example.
You can do gravity for two different elevations, right? I mean, height
Yeah.
function. So you go from here to here, and then here to here. So a rectangle is a is a is a is a miniature of a closed loop, right? So a closed
Yeah,
loop
yeah,
can be expressed as a rectangle, right? Systemized as a rectangle, right? So you go from here to here in two different paths, along this path or along this path. This is the same as going from this point to this point along this path and along this path, right? The difference is that this is smooth and it has edges, right?
yeah, yeah.
Does it make sense? So
Uh,
in topology it doesn't matter. Topology, the edge doesn't matter actually. I mean, you can smoothly deform. I mean, you can actually make this. In topology, you can actually deform this thing into a circle. So you can just smooth out the edges, and these are called deformations. So you can continuously deform things and make it this way. Anyways, this is just a fun part. But Mr. Fakhrujaman, is the example clear? Why we did this? Why we
Yeah.
considered the rectangular construction? Okay, so that's one construction. There is another construction which is technically more powerful again because of its computational elegance, elegance and powerful because it's computationally sound. So the second
Sorry, by
approach.
the way, can you please save this Jamboard and then send it, because I couldn't follow a few things. I mean,
Can I send the Jamboard?
Yeah, yeah.
Yeah, sure, I can send this.
Thank you.
I think all of my lecture notes should be available. I think Rahul has it, which I wrote in the class. Yeah. So
This
we
one is
will make them available. All of them. But obviously this one I can upload because it is with me, but the others are not with me.
yeah, sure.
And actually others I want them as well. The notes that I bring, they are horrible. Construction of a potential of phi, say potential function phi. So I'm just using phi for that by use of indefinite integrals. Okay, so this is another construction. The second type of construction. We did the construction of open rectangles. Now this is so. By the name of it, you can see this is a indefinite integrals. This basically means it's some computational stuff. So let's delve into it. Suppose you have explicit examples. Let's work on R3. And we have an explicit example like a vector field can be expressed like this. In R3, you should have three components. So the gradient should be like this. F1 should be d phi dx, F2 should be d phi dy, and F3 should be d phi dy, right? And so it is continuously differentiable in S in R3. So these are also in S in R3. True for that region. Using indefinite integrals and integrating the first of these equations. Okay, so I integrate this thing. Integrate it. So if I integrate, what should I get? This is indefinite integral. So I need to, if I integrate, I should get a arbitrary YZ constant, right? Because I'm doing, yeah. Right.
Yeah, yeah.
Okay. But then I integrate the second equation, right? I'm sorry. Can I do it that way? No. Let me call these names. Ek, dui, tin. Ek, tabi. X, Y, Z. So if I integrate over Y, let's see. In the particular integrate query, we find in black I used to do this like when I'm teaching, sometimes I switch languages. Then there are some foreign students, and they just complain to me, like, "Sir, I don't understand what he's saying." Yeah, so we have these three things. Now the point is that you have three arbitrary functions here, and you see the three arbitrary, they are not arbitrary. Can you see why they are not arbitrary?
They have some symmetries.
They give you the same thing.
Yeah.
They give you the same thing. So they are almost always found by inspection. Okay. So this is how you can find phi. Okay. If you have a gradient, then you can find phi by just writing down the components and integrate them. And integrating them, you find this. So if you this is okay. So this lies heavily on the fact that you can integrate this thing. That means this f1, f2, f3 are nice functions. They are integrable, but they are not computationally too challenging that you cannot do them. So if you can do them, that's good. But you also need to worry about this arbitrary function. This is not a constant, really. It's a constant of integration, but this is an arbitrary function. So you have to worry about these arbitrary functions. However, these arbitrary functions are almost always can be found by looking at these three equations, and you have to satisfy them. So just inspection you can solve it and find it. So there's an example in Apostol. This is like in page 344, example 3. So please do this example and you see that how powerful this is, because you just look at them and you find them. Because they all need to give you the same phi. Okay, they all need to give you the same phi. So you just know whatever this is. So this is missing here, right? In this expression, A contains yz, some function you don't know. But this contains more information, right? So this yz could be found from looking at this term. Okay. Then you look at this term. Then this xz could have something to do with this term and this term combined. So this is how you can just look at them and see, oh, acha, if you pick certain combinations of this, if you pick certain expression of these things, okay, then you see the combined thing will give you phi, which is compatible with all these three, all three of these. So that will help you to nail down the function. That's the trick. Now the most important example, okay, construction of a potential on a convex set. So the most important star. Convex set idea is very important. Construction of phi on a convex set. Do we know what is a convex set?
Yeah.
So Banglar Patch. Is this a convex set?
No.
It's not a convex set. Is this a convex set?
No.
Is this a convex set?
Yes.
So any 2 points you can join by a line. That's a convex set. These are not. So, okay, so this is a path which joins point A and point B. So your path alpha starts from A, and there's a T which joins point, you can call it a B, so it's a B minus A. So if you want to have this point a variable, so you fix one point and let this point vary everywhere. So what you do is you call this X. Oh, come on. Then so this is your this is a path on that convex set S. So this is the convex set. what is t bounded? T is bounded from 0 to 1. Oops. Good enough. So what is alpha prime of t? Just x. No, x minus a. So what you want to do is you want to compute this. No? If the gradient exists, what I mean by that is that if vector field is a gradient of phi, then you can find phi by integrating it along the curve. So the curve is that, so you have a d alpha, which can be written as f dot alpha prime between 0 to 1 dt. What is it? It is nothing but, you have to express it in this way. So it's 1. It's a function of alpha t. Remember, this is nothing but alpha t, which means it is a plus t of x minus a. What is alpha prime? Alpha prime is x minus a. So if you take your a to be the origin, so let a to be the origin, some n tuple of zeros, and this becomes f. So this becomes a zero vector. This becomes a zero vector. I shouldn't do that, but I'm just showing you. So this is dx, and there is a zero vector, so we have just dotted with the x vector dt. Okay, that's it. It has a very nice looking expression when you're computing it with respect to the origin vector. Okay. Now we will use this one and a bunch of other things to prove the most important results of today's class, which would be potential functions on convex sets. And one of the proofs, I'm going to leave it to you because it's a very straightforward exercise with a little bit of a subtlety out there, but I think you will be able to handle it. Mostly I'm going to skip it today because of the time constraint, but I'm going to mention the tricky bit. Okay, please bear with me and let me know if you have any questions. So what do we want to do? What is our goal here? Why am I saying that this is important? I'm going to use it. What is driving me forward? So in this discussion, we have learned how to construct potential functions in some interesting ways. So we saw three different ways at least. One was open rectangle, one was using indefinite integrals, one was geometric and basically considering a closed path and using a better rectilinear path to do that, which gives us more clarity on the path and more clarity and more control over the paths and integration. Second we did was on indefinite integrals. So we saw that we get some arbitrary functions and they are basically can be solved by inspection. And the third was on the convex set. So these are three interesting ways to construct this potential function. Now remember that we found a necessary condition for, we are trying to test what vector fields can be expressed as a gradient of a scalar field. The scalar field is called potential. And we said the necessary condition was, remember, the necessary condition, NECEWY, necessary condition was this. DIFJ is equal to DJFI, right? This was the necessary condition for a vector field to be a gradient. Now, is this a sufficient condition? We met that this is not true. That okay. So we saw that. Well, we didn't see, but we didn't. We can actually come up with. We can actually come up with an example. So we did one example. No? I think I haven't mentioned it properly, right? In that example, that we checked out that the example that we checked out, this one, was more interested about showing that this is not a gradient, but I probably didn't say the important point of this thing. If you compute DIFJ and DJFI of this thing, you would find that this is equal. Okay, but as we have shown that this is actually not a gradient, no? Why it's not a gradient? Because the integral was not the closed integral was not zero. So this is a counter example that this is not sufficient. So what is the sufficient? So you ask the question, what is the sufficient condition? Is there a sufficient condition that we can make this work? With this necessary condition, is there some sufficient condition that we can impose which will help us to nail down a vector field, which is a gradient? And there is. And this is the idea of convex sets. That's why the convex sets come in. So the sufficient condition can be proved for convex sets. So for that, we need a very special result. So to prove the sufficient condition, we need a very neat, I would say, neat or say tricky result that goes by the name of differentiation under the integration sign. Usually mathematicians are very careful when you do differentiation under the integral. Suppose we have an integral of dt and you have a differentiation with respect to dt, and you just can't go ahead and say, oh acha, I can just do this. Okay. You can't just go ahead and do this. Okay. So here we will find a very nice proof which helps us actually show that this can be done. So let's, without further ado, let's write down the theorem. So theorem is this, that is a convex set open set or closed set? Anyone?
Convex sets are open sets.
What is the definition of a convex set? Why is that an open set? When we said that any 2 points can be joined by a line, right? The definition was that every pair of points in S can be joined by a line. So every open convex set is connected. But does it have to be always open? Can we have closed? Can we have closed convex sets? Convex sets, so that.
Not sure.
Yeah, they can be closed as well.
So if you subsequent, the whole line is joined. Equivalent convex is a convex unit set. Solid cube is a convex set, but anything that is hollow has an indent. Boundary of a convex set is always a convex curve. The convex means convex analysis, then convex can analyze square bit. Well, the order field. Set C is absolutely convex if it's convex and balanced. Only with epigraph region in a graph convex. Okay, you can have open convex set by just declaring it. Closed convex are convex that contain all of its limit points. And you can make it open or closed. You can have closed convex set. I couldn't see a problem. Anyways, that's all right. So why was I saying considering open or closed set? Because now we are going to consider S to be a closed set. Let S be a, for the theorem, we want to consider it, be a closed interval in Rn with non-empty interior, and let J be equal to some interval in R1. Sorry, if I say interval, this is not helpful. set subset. Okay. This is also closed in R1, needless to say. So Jn plus 1 if I consider. Okay, what is that? So obviously Jn plus 1 is a closed interval which is contained in where? Contained in S cross J, right? Okay. Does it make sense? Which is itself contained in Rn plus. If I say S cross J, that is equal, right? So this is equal actually. That is contained in Rn plus. Does it make sense? Do you see what I'm saying? As be a closed interval in Rn and J is R1. So S cross J is Jn plus 1.
Sorry, I'm not following. Is it an element or subset notation? So
Which one? These are subsets.
But J is not. J is also an element in Rn, right? No?
J. This one is it's not Rn. No, this is a interval. This is in R1. Sorry, I just my one went away. I don't need to write a one, right? This is a
Okay. So
close
Rn.
subset of R. Close subset of R.
So is this close subset actually?
Yeah, close subset. Yeah, this is subset notation.
Okay. Oh, I thought it's an element. But so why it's not an element? I'm just curious.
Okay, so this is this is also if you R is okay.
It
So
can be an element as well, no? I mean, just grammatically speaking, because
yeah,
an interval
but
can also be an element,
yeah,
right?
but these are then we okay. So the idea here is that we have an R, right?
Yes.
Actually, you're right. There are also elements, but in a different sense. You have these points here, right? These points are element of R, but this also has points. It's a collection of points. So
True.
it's like a sub. That's why it's called subset.
Yeah, subset. True, but
Yeah.
but a set can be also an element of another set. But I'm sorry. Maybe.
Yeah. You're right. Yeah, but we when you have a collection of elements, okay, then we call that a subset.
Usually, yeah, that's the notation. So there must be some reason. That's why I'm asking.
This is the reason that it forms a set itself. This is a set itself, right?
Okay.
So yeah. So in a group you have a subgroup. So so if it forms a set itself, then you can call it a subset, right?
That's true.
It's contained in R.
Because I see sometimes it's being used interchangeably, so then I get confused here.
Yeah, but you have a feel for it, and then unless this is very subtle issue. I don't think here it's a very subtle issue.
Okay. Thanks. Sorry,
I think an element is not a set, but if you bound it with brackets, then it becomes a set. Like that is what they usually mean.
Yeah.
Then you can call it a subset.
But that's a notation, right? That's a notation.
Yeah.
No, that's the notation part. I'm talking about the interpretation.
Yeah, every single thing is an element, right, of R, and also in this case of J, right?
No, if you write it, then it's a subset. Like they say it like this way. But if you take
this is J. This is an element of J, and J is a subset of R. Does it make sense?
Yes. True.
That's how the distinction is. If you have an individual element, then you call it element, and then if you have some set. Okay, so we write each point in this set. Each point you write it as x comma 2, where x is coming from this space S, which is a closed interval in Rn, and t is coming from the from the J, which is actually in R1, which is just a one closed interval. So
are you multiplying S product J, right?
This is a Cartesian product.
Cartesian product. Okay.
So so this is like an element xj would look like this, xn comma t, right?
Okay.
So this is our given. So this construction is given. The next thing is that psi is a scalar field defined. So psi is a scalar field defined.
Sorry, can you just go up a bit so I couldn't just copy it? Yeah. Okay, thank you.
Yeah, I will upload this one as soon as the class. Just follow.
So it is Rn plus 1?
Which one? This one? Oh, because S is Rn. S is Rn and you are Second
Yeah,
Cartesian product with J.
so it goes
So,
there. Okay.
so if you have R times R, you get R2, right?
Got it, got it. Thank you.
So psi is a scalar field. Yeah, please ask questions. There's no harm in asking very simple. If you think it's a good question, but these are good questions. Please ask. Yeah? Should not keep anything confused in your side if you can clear up. Right. The psi is a scalar field defined um, on. Sometimes the questions are not that trivial actually. Not so easy to answer. So that's very important. We have more questions. Psi is scalar field defined on this. Okay, on this space, on this set. Such that the partial derivatives, such that dk psi, these are the partial derivatives, this is continuous. Yes. So Riaz, when you have partial derivatives continuous, what does it hint us? What is this license for? When you have a bunch of partial derivatives and they're continuous in a region, it gives us a license to use what? Also in a closed interval. Mean value theorem, right?
Yeah, yeah, yeah.
It gives us a license to use mean value theorem. Where k is some index taking n value. So define a scalar field phi, define phi, এটা assume করি, let করি, phi আমরা define করি, phi অবশ্যই argument important. A থেকে B phi আমরা define করতেছি যে একটা scalar field integral আরেকটা এবং partial derivative তাহলে এটা আমরা define করছি তাহলে আমরা বলছি যে then তাহলে এগুলো হচ্ছে আমাদের থিওরামের কন্ডিশন তারপরে হচ্ছে থিওরামের স্টেটমেন্ট then dk phi exists. We started with dk psi, continuous dk psi. Now we define phi and we said dk phi exists at each point bolte each interior point bola uchit, interior point of that closed set S, okay, and you can write dk phi of x to be equal to AB dk psi x vector t. That means আমরা যেটা করছি এখানে আমরা বলছি যে এটার উপর ডিকে নিলে আমরা এইভাবে লিখতে পারি তার মানে ডিকেটা কিন্তু এখানে এক করবে তাই না তার মানে আমি বলছি যে এখানে এক করলে এটা ভিতরের এক করার সমান হয়ে যাচ্ছে আমরা বলছি যে ডিকে from psi the same thing as dk I think inside so we are interchanging the order of indication. However, there is one, it is intuitively clear why I can do this. Can anybody give an example why it is clear that I can interchange the integral sign?
Because x and t are independent.
Yeah, that's independent. So integral is over t and dk is over the space, right? So they're independent, right?
Yeah, yeah.
Yeah, that's good. So the theorem proof is I left it as an exercise. It is a standard thing which this kind of proof we have done before. So please go through this and if you get stuck, let me know. Proof is very simple and intuitively you can see that this can be done. So we are going to use this one to prove the final glorious result that we are looking for. That is the sufficiency. Technically, this is what you're looking for, sufficiency condition. That gives us this technical tool to use this on a convex set to say exactly that if this condition is satisfied, then obviously the function is a gradient. If this is not, then this is not a gradient. So the theorem is this: let f is equal to I think let me write it as sufficiency. Sufficiency condition. Please excuse my writing. Like a cockroach walking over there. If I can do better. B A continuously differentiable vector field on an open convex set S in R. Then F is a gradient unless if and only if we have so it contains both of them, right? If and only if. So sufficiency টা আসলে আমরা proof করব, necessary already done. So let me briefly do the proof. Proof this necessary part is has already been done earlier. Done or instead of done topics. So now we go to the sufficiency part. And you just go ahead and write down this thing. Remember this? Remember this? Remember?
Yeah.
And this was construction in open set, sorry, convex set. We are going to just take this and move from there. So let us define this to be psi. We need the psi so that we can apply the previous theorem we met earlier. So this is a closed and dimensional. So when you write this, what do you mean? So if T is closed and contained in S, does it make sense to you? This is a convex set. This is a closed convex set, right?
Yes.
Contained in S. Okay. Then psi, okay, can be considered to be defined. Psi is defined on T times J, right? There is a T, this is coming from the J. Do you see that? This 0 to 1, it is coming from the J. This is coming from the T. This is coming from the J. 0 to 1, okay? So this is this. That means if it is defined on this, that means our statements or conditions of theorem that we met earlier, we call the theorem 4, is satisfied. That means we can use the result of that theorem. That means dk. So this is how I define phi of x psi. So এটা তো আমাদের আগে theorem ছিল যেভাবে define করতে হবে। তার মানে হচ্ছে যেহেতু এটা কন্ডিশনে ফুলফিল হয়েছে, we can say that dk phi exists. Okay, and how? What is the form of dk phi? We also know that. That is nothing but this is what the theorem told us, right? This is what the theorem told us. That if your psi is defined on this thing, which is Jn plus 1 is nothing but the Cartesian product of S cross J, which is a closed interval, okay, closed convex set, then you have this stuff. You can write this down and then dk phi exists. That we are just taking this result. Okay. Now the rest part is to compute decay psi. A decay psi computation is very easy. We have a psi which is given by what? This expression is given by f of tx dot x. We have to apply this operation on this thing, but that is very easy. Once you apply on, if you apply on tx once dot x and another time you apply on dx. So this is the x, means these are coordinate vectors. These are e1 I e2 j, right? Does it make sense?
Yeah, yeah.
Coordinate vectors. So this will be nothing but so this factor should be ek because you're, yeah, so শুধু ওইটা, I'm sorry, ডবল নোটেশন ইউজ করে ফেলছি সরি, এখানে আমি যেটা করেছি এটা একটু কাজ। এই এক্সটা আসলে হচ্ছে এক্স e1, রাইট, y e2, নাও ডাজ ইট মেক সেন্স? তো এই ডিকেটা আসলে হচ্ছে এক্স এর সাপেক্ষে হলে এক্স কে ইয়া করবে, ওর ইউনিট ভেক্টরটা আমাকে দিবে। ডাজ ইট মেক সেন্স না?
Yeah.
Previously I just got carried away with that and wrote the unit vectors twice. Sorry about that. Now that is done, this part is done. What about the first part? What is this? This is not
We are
nothing
just
but
getting a T out. It is like the homogeneous function.
T out.
We are just getting a T out.
How is that? We haven't said function is a homogeneous function. This function
Oh
is
no
not
no no! It doesn't necessarily have. It doesn't necessarily be a homogeneous function, but homogeneous function could be an example for
no,
this
this is
case.
not. This is not nothing to do with homogeneous.
Yeah, yeah.
Don't do that.
We would get some powers of T for every partials.
So it will act on all the components, right? This first thing is clear. So it act on all the components.
Yeah, yeah.
So what you can do here, you can apply. So what you should do here is that you should apply chain rule here. So what is the chain rule here? So let me demonstrate for one of them. One of them. Suppose I have a dx acting on f dx. So what I do is I take the f, sorry, partial. এটা আচ্ছা আমি একটা জন্য দিলে তার partial হবে। Do a total derivative example. Yes. Yes. So, alright. So this function changes if the argument changes. So with respect
It
to the
should be
argument.
Tx.
Well, it's okay. So okay. Now I have to do partial. Sorry, it can't be tx. Sorry. Let me have this thing. When I'm taking derivative with respect to x, I'm considering t fixed.
Yeah.
Okay. So this function changes if only x changes. Okay. Then I go ahead and take the derivative. But can the chain rule work like this?
No, no, no. It has to be Tx because if x changes, Tx also changes. Then we can apply the derivative on Tx.
Yeah, but x changes, tx changes, right? X changes, tx changes. That's true. If x changes, tx changes. However, the question is, so it's a okay. They will act on all the components, and It is not clear actually. Why is that true? You can't do this.
Yeah, I have a question here.
Yeah.
Our f is a vector value, f is a vector field, right?
Yeah.
F of t of x. And if I'm taking partial, then isn't it supposed to be a Hessian? And then I'm taking a dot product, like
Which one? Which one?
the first term, yeah, yeah. Isn't it supposed to be a Hessian? Then I should get
Why?
a Hessian with and a dot
Why is
product.
this a Hessian? Why there is no second derivative? Why is this a Hessian? This is the first
No, no,
derivative.
no, because it is a vector field.
So what?
Yeah, yeah,
When it's
yeah. It is a vector field, right?
yeah, we
So
have
if I
first
take
derivative.
so
When it's
if
a
I
vector
take
field,
part
but yeah, Hessian is the second derivative. Vector. Okay, I understand what you mean, but you haven't.
oh
We have
Jacobian
not.
matrices. Sorry, my bad.
Yeah. So
It will be Jacobian matrices. Yeah. Then I
yeah. The okay. So but Jacobian matrix is not for decay. It's for the total derivative.
yeah.
Okay. So why the t is out? I'm not sure. It should come from some chain rule stuff, but how to show that it's coming from the chain rule stuff? Tx, so tx over. I think it should, yeah. So it changes, then it should be this then. But I'm taking with respect to x. So yeah, I think that's right. Probably that's the thing. So you have to somehow come to this. These and these are not, yeah. So right. So this should be dx. It should be dx. Only then one can get this. Only then one gets the t out. Now we have to find a interpretation, which is so. How is this true? So let us look at the chain rule. We had the chain rule defined, right? Let us remember what the chain rule is. Do you know how it was defined? That g of t was if g of t is
It, it was alpha of t, but
which
it
one?
is for scalar field. Here we are doing for vector fields.
No. We're doing for components.
Oh,
Let's say
okay,
we're doing
okay.
for
Then
components.
we can do for scalar fields.
Yeah,
It
but
will be
chain rule is
alpha of
for yeah.
t.
Yeah, chain
It
rule
will
was
be
for
alpha.
yeah. Chain rule was for scalar fields, right?
Yeah.
You're right. So give me a few seconds for. Let me just try and nail it down. Well, just I have to find the page where it is. Even I forgot exactly how GT was defined. Yeah, I found it. So GT was f of r of t, right? If you have this, this is easy. This was the case, no?
Yeah.
But in that case, you had a derivative with respect to t. Okay. Here we do not have a derivative with respect to t. Here we have a derivative with respect to x. Okay. It's not a gradient. We will use this result ultimately later on. But here, if you have a partial derivative with respect to t fixed, then we're saying that dk acts on all the components, and we're saying that this changes, this argument changes when x changes, this changes, function changes, and so here f changes. Let us think of this way. F changes if the argument changes. Argument is, so let us look at this way. Maybe we can use this one as an example in a different way. So f changes if r changes, right? So this is the term. R changes, f changes. Then because of the derivative here, the r changes by this. Similarly, here f changes if this thing changes. So f changes, this thing changes. This thing is this thing t for fixed t, it actually changes if x changes. So f changes if x changes, and the argument has tx which changes if x changes, then tx changes. So then you have this thing. With respect to change of dx, your argument changes. So you have a tx, argument changes. So that's why these, in the chain rule, these two doesn't have to be the same. In the chain rule, they don't have to be the same. This is what Hasutsa was telling us. They don't have to be the same. So for a fixed tf changes if x changes, and the argument changes, also the function argument changes if dx changes. Does it make sense? Does this interpretation make sense?
No.
This is ftx. This function changes for a fixed if x changes.
Yeah.
So you want to calculate its partial derivative. Okay. You want to calculate partial
Then it should be
derivative.
gradient of f dot tx.
Now gradient of f, where is the? It's only dx. It's only one. There is only
Yeah.
one x. There is no gradient here, right?
Yeah.
There is
Yeah.
only one derivative, one partial derivative. So this function will change if the argument change, right? Argument change if x changes. Because t is fixed. You even can consider t is not there. Suppose t is not there.
Yeah, if t is a constant, then of course it
Yeah.
will just come out.
Right? So
Yeah.
if t is there, then you just multiply with it.
Yeah, just it will just come out. Yeah.
Does it make sense? Okay. But if there is a t there, then this should be there, right? Because the argument has a t there. Okay. So let us try to establish that through chain rule. It has to be a chain rule. Chain rule differentiation. Wikipedia has that. If h of x is f of g of x, then h prime of x is f prime of g of x, t prime of x. Okay. So intuitive explanation, history, statement. Simple chain of variable function is one real variable. It says a g is a function is at a point c. You have this. But here y, the function, these are only single, there is no constant multiplied there. So quotient rule, there is single function. Okay, I will leave it for your check, or I will.
Yeah, it's actually
This,
chain rule. Yeah, it's right.
you should be able to. You should be able to show this.
Yeah,
So,
yeah. If you don't mind, maybe today we can.
yeah. I just, it is done. I just give me. Can you give me just 2 minutes,
Yeah, okay, sure.
if you don't mind?
Yes.
2 minutes. Sorry, I took too much time. I understand. Today is Friday, and I'm taking too much. I have taken too much time actually. Just one or 2 more minutes, and I'm done. So once we get this, then we have proved. We have proven. So we have this. So our result was that you can now write this in this line. We can write t dk acting on all these components. So instead of dk acting on all the components, f1 to fn, dotted with, so there is a problem with the dot. So okay, so what is happening is that you have a t and you have a dk f1 dnf dkfn, sorry, dkfn, and in case of x you write x1 to xn, and just tuple expressions. Then because this is a dot product here, okay, this is a dot product here, and okay, not because it's a dot product. So we take it from there. So this is equation 1. I'm just going to rewrite this equation. So I'm equation 1 take our likhiyo is at. So I'm just writing this dk psi to be equal to I found a t dk f1 dk fn dotted with x1 to xn, right, plus plus we found f dotted with ek with tx. So now I'm going to use one thing. We know dk f1 is d1 fk, right? We found this theorem, right? Is it okay?
Yeah, yeah.
I can change everything like this, right? Now I have a, so I take this and this side just sits. Now if you take a dot product here, what happens is that if you take a dot product, what happens is that you have a d1 fk, dn fk, x1 f xn. Well, isn't this your it should be your, if you take it, so okay, so what is this? You have a d1 fk and x1. This should be your total. This should be your, so let me write it down, then you'll see d1 fk x1 plus d2 fk x2. What does it look like? dn fk xn. What does it look like? And এটা বসে গেছে, that's the way it is. Doesn't it look like this? Doesn't it look like this?
Yeah, yeah.
So we're done. We are almost done. So হয়ে গেছে আর কি। তাহলে এখন আমরা জানি যে we know what it is. Why? We know what it is because if you define g of t to be fk of tx, right? Then g prime t is, we know this thing, right? We have just written down. This is nothing but this times x, right? So we just plug this in there. G prime t plus f dot ek for shorthand. I'm just running late. The next is that you can do it. You have a dk psi here. Next what you do is you so dk psi you have this formula, and then, well, this is the, আমি তো already define করছি this to be g, right? So you can write this as g as well. So okay, you can write it as you can write it as g, or g যদি scalar, so আমি তো fk কে define করছি, এটাকে define করি, but f dot ek মানেই তো fk, এটাতে f dot ek, এটা মানে তো fk, এই fk tx মানে তো হচ্ছে gt. So you have a gt and tgt prime, or g prime t, sorry. So next what you do is just integrate this thing and you're done. So just go ahead and integrate this dk psi from 0 to 1, and I am pretty sure you can do this. And when you do this, you end up getting g1 minus 0 to 1 gt dt. Okay. When you do the integration, you get this. So what is this? Well, if you plug in all this calculus, actually you do not even get this one. This part cancels out. When you do the full calculation, this part comes from the other part and it cancels out the, when you do the calculations, you have to integrate over this part and this part. So you do integration by parts, and one part of this cancels on another part of this, and only term remains is this term. So this is nothing but fk t equal to 1 is x, which is your dk of phi. So you have been able to show that dk of phi is indeed fk. That means f is gradient of phi for each component. This is true for all k. So this is true. So it all boils down to you being able to do this integral. Okay. Thank you. Sorry, this is where I am today.